often see that um, that people insert some kind of symbol here. For example, you may see that there's a big T at the beginning and then a bunch of operators. It simply means that you insert operator according to that time. So insert the operator that's more in the past first, and then the other one and the other one and so on. That's it. Very well. So now let's see how we can compute all of these correlation functions, I should say transition amplitudes, at once. So in order to do so, we will modify our Hamiltonian a little bit. So we started with some Hamiltonian that was a function of P and Q. Now let's modify this. So we keep what we had, but we add something to it. So take a completely arbitrary function, f, a function of time. And another completely arbitrary function, h. I'm omitting g because g looks like metric. Okay. So these f and h have no physical meaning, right? So q and p are, of course, position and momentum, but these are completely arbitrary function. So what do we gain by doing this? So what we get now is that our path integration now becomes dp, dq, and we don't even integrate over f and h. So there are some fixed function. And then we have I. Okay. So this is now our path integration. This was the transition amplitude. But to distinguish this transition amplitude from the one that we had previously, because now we have this modification, let's denote them by f and h. So this is the transition amplitude when we have modified our Hamiltonian by adding this extra bit. And this extra bit has no physical meaning because we said that f and h are some fixed arbitrary functions. All right. So what is the point of doing this? And of course, I mean, just as a comment, the thing that we really want to compute is nothing but q double prime, t double prime, possibly with operator insertions, q prime, t prime at 0, 0. Because at the end of the day, we will set f and h to 0 because, again, they have no physical meaning. But before we set them to 0, they allow us to take derivatives with respect to them. Okay. So what I mean is that this object depends on f and h. Because f and h are not integrated over, right? So there's some fixed function. So we can vary them. And what happens if you take derivative of this with respect to f, let's say? Okay. So we act on this thing with the functional derivative at some time t1. Okay. So let's see what happens. So again, even though these are functional derivatives, in practice, you can treat these as just ordinary variables, the argument of them as ordinary indices. And whenever you are integrating something inside an integration, you take the derivative and then you forget about the integration. Okay. So since there are no integrals over f and h, this derivative will go right to the exponent, to the exponential. And derivative of an exponential is the exponential and then the derivative of the exponent. And the derivative of the exponent is very simple because it is linear in f, right? So you will simply get the coefficient of f. So everything is as in ordinary differentiation. So the answer that you get after you take this functional derivative is The integration remains as before. What you had in the exponent also remains as before. And then you add what you get by differentiating the exponent, which is nothing but the coefficient of f evaluated at the same time as t1, right? Because recall from our discussion on functional derivative, what was that? Right. So recall that here we had a very similar integration. We had something linear in f, we differentiated with respect to f. What we got was the coefficient evaluated at the same time or argument as the argument in the derivative. So now you just get q evaluated at t1. But this is nothing but this, right? Without this thing. So this is q hat acting at time t1. And we still write f and h because they are still f and h. But as we said, we don't really care about f and h. So when we want to actually compute something, we will set f and h to 0. So set f and h to 0, replace them with 0. So that replaces them here with 0. So you forget about these terms. And then what you're left with is exactly what we wanted, right? You have the usual path integration with the usual action and this additional insertion that corresponds to this operator insertion evaluated at 0 and 0. Okay. So the point is, if we take functional derivative of the transition amplitude evaluated at f and h, and then set f and h to 0, what you get is the transition amplitude with the operator insertion. Okay. And you could repeat this derivative multiple times, right? So you can take another derivative at a different time, q2. And once you have taken all the derivatives that you want to take, then you set f and h to 0, right? I mean, if you set f and h to 0 after taking just one derivative, then you cannot take another derivative. And this gives you two operator insertions. Right? And similarly, if you take derivative with respect to the other arbitrary function h, which was the coefficient of p, you can already guess what will happen. You simply insert p hat at time t2, right? So notice what is happening here. You can cook up any operator insertion at different times. There can be arbitrarily complicated operators. The way that you compute this transition amplitude is simply that you start from this modified transition amplitude with non-zero f and h. And then for each operator that you have here, you put a derivative here. And once you have taken all the derivatives that you need of this modified transition amplitude, you set these extraneous functions to 0. And then you end up with exactly the transition amplitude that you wanted to compute. Okay. So let me write down a slightly more general formula. So suppose you want to compute, suppose there is some arbitrary function of p hat and q hat. Then here, what you insert is the same function, but now function of derivatives acting on the ordinary transition amplitude with the modification. And then you set fh to 0. All right. So what I mean by this notation is that, so if f p hat q hat is just q hat at time t1, then f, I don't want to write f so many times. So let's say f del. So let's make a table. So what I mean. So maybe the operator that you want is just q hat at t1. Then the thing that you insert here is just derivative q at t1. If the operator is q hat square at t1, then it's the second derivative. The operator may be, let's say, p hat at t2, then p hat at t1, and then q hat cube at t1. Then it's the same thing, but with derivatives. So del cube, del q t1 cube. Okay, so this is the correspondence. So this is what I mean. Take any operator that you want, built out of p and q at different times. And on this side, replace each operator with the corresponding functional derivative. All of these derivatives will act on this object with f and h. And after taking the derivatives, set f and h to 0. And that will give you the transition amplitude that you really want. Okay. So this is an important formula that we will come back to again. So let's make sure that this is clear. So yeah, if you have any question, please ask. So there's one question in chat.
Sir,
so what happens? Yeah, go on.
Is there any way to understand what's the physical meaning behind the taking the functional derivative that gives us the operator? I mean, why taking functional derivatives gives us the operator?
Well, I mean,
is there any way to understand this from the picture that you drew yesterday, or is that total mathematical step?
Well, it's kind of both. So it is true that it is mainly derived from some mathematics, right? So as I said, that you can start from the discrete version where things are very clear, and then you can arrive at the continuum limit, and the functional derivative is what you will end up with. But okay, so the main thing that the functional derivative achieves, so what it does is really that it just inserts a copy of whatever you're taking derivative with inside the integrand, right? So that's the main modification that we want to do. So taking a functional derivative is equivalent to inserting this this function inside the integrand.
So it's total mathematical step.
Well, so yeah, I'm coming to that. But the first, you have to understand that this functional derivative is nothing but this insertion, right? So now you can ask why this insertion corresponds to this operator. So one way to visualize this is that, so your state starts here, right? At time t prime, it starts at q prime. Then it evolves in some path. Then at some time t1, you're acting with an operator. So an operator is going to measure something. So if the operator is, if it's the position operator, then it's going to measure the position of this path at this time. And what is the position? It's just q at t1, right? Where q corresponds to this thing. So for each path, you simply have to insert the value of that at that time. So if you have some other operator, you are going to measure that operator at that time. So, and the operator is going to give you some value. So then insert that value and then keep on going. So you do this, you insert some value here, and then you keep going. So what it ends up being is that the same thing, the same phase that you would assign to this thing, but with the insertion of some value at this time, and that's it. So that's as much of a physical picture as you can get. And this insertion is achieved by this functional derivative. That's just a mathematical fact.
Thank you. Another question.
Mhm.
The value of functional derivative is a function or number?
The value of the
The-
functional derivative at a particular time is a number, but that number depends on both the time and the path, right? So it is a number. I mean, if you take a path q and you evaluate it, so what is a path? A path is a function. So if you take a function of a single variable and you plug in a particular value of that variable, what you get is a number, right? But of course, it's a function in the sense that to get a number, you have to choose a path, first of all, and then we have to also choose a value. So there isn't a big distinction between a function and a number here. Is it clear? I mean, let's say that, I mean, suppose you are doing like, you are integrating x, right? From -1 to 1. So is this a number or a function? I mean, of course, f of x equals to x is a function. But if you evaluate this x at a particular value, at 0, what you get is 0. So that's a number, right? So each function gives you a number once evaluated at somewhere. It's just that.
So it's a function of time, but after that, after the evolution, it will give the value.
It's a number, that's right. The main point is that it's not an operator. It's an ordinary function. All right. So is this dictionary clear? Oh, sorry, there was a question. So what happens when the arbitrary functions are nonlinear in Q and P? Well, I think so. This is an example, right? So you have Q cubed, P. So you just have higher order derivatives. So nonlinear functions means nonlinear derivatives. All right. Hopefully that's clear. Okay, now let's see.
I have a question.
Yes.
So does this procedure only apply to functions of Q and P only, or we could like apply this to other operators as well, which may not be functions of Q and P?
Such as?
For example, yeah. So
And
think
probably
about it.
you have a different scenario in mind. Because in this particular example that we are discussing, there are only two basic variables, so Q and P, right? So the phase space of a single particle moving in one dimension, in one dimension. It only has two variables. So one is Q, which is its location in one space dimension, and its momentum at some time, right? So then any other observable that you can build up must be a function of these two variables, because any observable is a function on the phase space. So if your phase space has only two coordinates, P and Q, all functions are functions of P and Q. But you may have a more complicated physical system with a bigger phase space, and then observables are going to be functions of all of those coordinates over phase space. And then you can, of course, insert those things as well, and then you would also have derivatives with respect to all these other coordinates. So basically, any function of phase space, any derivatives with respect to coordinates of phase space.
And there is
Does
no
that
condition on the arbitrary functions f and h because we are just taking them to be 0.
Exactly. Yeah.
Okay, thank you.
Yeah, no problem. All right. So in practice, I mean, if you're doing some kind of physical computation, this is the kind of things that you will compute with arbitrary q prime, arbitrary t prime, and so on and so forth. However, textbooks often simplify this problem even further. So what I mean by simplification is that, so when you were computing these things, you were doing some path integration, so like this. But again, you have to remember the boundary conditions that at time t prime, q have to be q prime, and at time t double prime, q has to be time q double prime, right? So, and these boundary conditions are extremely important. And in research problems or in practical applications, they are often the kind of things that you worry about the most. But of course, in textbooks, we don't really have to worry about these kind of technical things. So one way to simplify these things is that you consider the limit that t prime is minus infinity. So it's your initial time is way back in the past. And similarly, t double prime is plus infinity. So the future is far ahead. Now, why is this a simplification? So let's look at the things that we were computing. So you start at q prime, and then you evolve. And then you take the inner product. Now, let's separate this into two parts. Okay. Let's see what happens to this part when we take this limit. So let's assume that H has eigenvalues E0, E1, E2, etc. Furthermore, we will take the lowest energy to be 0. If your Hamiltonian doesn't have the lowest energy 0, you can always add a constant and make it 0. But it has to be bounded from below, right? So with this modification, so what happens? So let's expand q prime into the energy eigenbasis. So you are summing over all energies. So n is your energy eigenbasis, right? So what I mean is that Hn is equal to En n. Now notice that, so this object, because this is an eigenstate of the Hamiltonian, you can replace it. Okay, so you just replace Hamiltonian with its energy. I wrote this incorrectly. This is the lowest energy. Okay, so when this is the ground state, so it has energy 0, then this is just 0, right? So for 0, you just get 0. But for any other state, even let's say even for the first excited states, this is positive because this is 0, everything else is positive. And t prime is negative because this is the limit that we're considering. So what happens? So you have exponential of something negative. Well, you have exponential of the imaginary number I, and then something negative. Okay. But now recall that yesterday we talked about Gaussian integrations, right? Actually, I have the lecture from yesterday, so let me go back. So this is the kind of integrals that we discussed yesterday. So this is the Gaussian integrations for a single variable. And as long as a is positive, this integration converges and we get some simple numbers. But we also discussed integrations where there was an I in front of this real number. And we said that we will evaluate these integrations by slightly modifying this coefficient. So we will replace this with I minus epsilon, where epsilon is a small positive real number, assuming a is positive. And then we get some kind of number. So really the reason is that this adds negative epsilon a x squared in the exponent. And assuming that epsilon and a are positive for large values of x, then you get an exponential suppression. Right? So that's the kind of trick that we play to evaluate integrations. So we will do the same here. So we will replace our Hamiltonian with 1 minus I epsilon Hamiltonian. Again, the whole point of doing this is that this will, so in the quadratic part of P, this will put now a negative coefficient. So that for large values of P, we have exponential suppression, and then we can do the integration over P. But if we do that, so what happens to this object? So with this replacement, this becomes e to the power I times 1 minus I epsilon En. Okay. So there's a phase still corresponding to I times 1 times this. So let's not worry about the phase. But what is the other part? The other part here is e to the power epsilon En t prime n, right? Now En is positive, as we discussed, for any state other than the ground state. And t prime is negative because this is our limit. So in that limit, this will always vanish. So whenever you have an excited state, so any positive energy, because t prime is large and negative, this is always going to vanish, right? So with this replacement and the limit that t prime goes to negative infinity, this thing becomes just the ground state, 0, and this, right? This is nothing but the wave function for the ground state. Let's call it psi 0. And more importantly, just a number. But the state that you have is the ground state. Okay? And you can similarly show that the other state, which was this thing, let me copy. You can just write here. You can also show that this object also projects down onto just the ground state. 0, again, with the wave function for the ground state. All right. So what you end up with in that limit, you can start from any transition amplitude. Q prime prime, T prime prime, Q prime, T prime. But once you take this limit that T prime goes to negative infinity, T double prime goes to positive infinity. And I will also put an epsilon as a reminder that we have to modify our Hamiltonian a little bit by multiplying this with an I epsilon. And then, of course, at the end, we will take epsilon goes to 0. But before we do that, this transition amplitude always boils down to the vacuum to vacuum transition amplitude. It's some vacuum at positive infinity and vacuum from negative infinity. And there are some numbers here. So what are those numbers? It's just these wave functions for the vacuum. But we will not worry too much about numbers anyway. So the point here is that whatever transition amplitude you have in mind, if you start from far past and you go too far enough in the future, it always becomes proportional to the vacuum to vacuum transition amplitude. Okay, and so because of this reason, people will often simply discuss how to compute vacuum to vacuum amplitude starting from infinite past and going to the infinite future. Okay, now what that does is that in our path integration, so now you don't have to worry too much about these boundary conditions, because previously we had these boundary conditions, but these boundary conditions correspond to the fact that our starting state was a position eigenstate and our future state was another position eigenstate. But as we saw, regardless of what state we put in as our initial and final state, they always project onto the vacuum state or the ground state if the times are infinite. So now when we do this path integration, we don't worry about boundary conditions because it's fixed to be vacuum or the ground state. And this time integration, this will always be from minus infinity to plus infinity. Okay. So this assumption just simplifies some computation, that we forget about the boundary conditions, we forget about the time interval, there are infinity, and the boundary conditions are that start from ground state and end up at ground state. All right. Okay.
What assumption? I'm sorry, this assumption?
Sorry, which assumption are you referring to?
You're saying this assumption just means boundary conditions.
Yeah, it's this assumption that you start from negative infinity in time, so from infinite past, and you go to the infinite future. So as long as you're computing a transition amplitude that spans an infinite amount of time, both in past and in the future, then this transition amplitude is always proportional to the vacuum transition amplitude. You don't have to worry about the boundary conditions anymore.
It's always vac.
Always vacuum, yes. As long as, again, you have to remember that you have to start from infinite past and go to infinite future for that to be true. Okay?
All right, okay.
All right. So now we will generalize this story to higher dimensions. But before we do that, are there any other questions?
Is that the same as vacuum expectation value, or is it?
It's not a vacuum expectation value because you are not computing the expectation value of an operator in vacuum at a fixed time, but rather you are computing the transition amplitude from vacuum to vacuum at different times.
Okay, all right.
Okay. Now, the generalization to higher dimensions, or what would normally be called quantum field theory, is completely straightforward. Because, so recall what we have been doing. So far we have said that we have a time direction. And at each time, we have a copy of one-dimensional space. And we have been computing amplitudes to go from one point in space to a different point in space in various ways. Okay. This is the picture, right? But this can be easily generalized in the following way. Instead of saying that we have just a single time and this one-dimensional space, we can easily add another dimension to this. So what we are going to say now is that, let's say, we have a two-dimensional base. They can be parameterized by t and x. And for each point, again, we have a one-dimensional space parameterized by, say, q. Okay. And in particular, for just a fixed time, so let's just fix some time t and allow all values of x so that you get a line now. And for each point, you have a one-dimensional space. So if you consider all of the space over this entire line to get a two-dimensional plane. Okay, that's fine. So basically, this 2D picture is now becoming a 3D picture, where the base is two-dimensional and the line over each point is still just a line. Okay. But we can play the same game that we have been playing so far, meaning the following. So what we have been doing so far is that we said that there is a function q over time, which evolves with respect to time. And at some initial time t prime, and at some final time t double prime, this takes some specific value, right? That was our boundary condition. But in between, we allowed all possible values of these things, and that gave us all these paths. Okay. But we can say the same thing again. So let's say that you have some function phi, which depends on both t and x. Okay. We said that the initial condition was that at t prime, this function takes some specific value, q double prime. Similarly, you can say that at t prime, this function becomes some specific function of x. Okay. So notice that we are still putting boundary conditions only on time, right? So if you have a function of two variables and you fix one of the variables, what you have is still just a function, right? And a function of one variable. And the way that we are putting boundary condition on this object is simply to say that at an initial time t prime, this function becomes a specific function of x. Okay. Similarly, we said that at some other time t double prime, this becomes some specific value. Oh, sorry, this was q prime, q double prime. Similarly, we can say that at that specific time, this becomes some other specific function of x. Okay. And then the way that we build the path integration in this case, we said that you take a sum over all possible paths that satisfy these boundary conditions. And for each path, you put a phase. You figure out some way of computing a real number out of a function of time, and you put that in the exponent with I to make this phase. We will now say exactly the same thing here. So we will say, do an integration over all possible functions of t and x that satisfy these boundary conditions. And for each such function, figure out some way of producing a real number, which you would call the action of phi, put that in the exponent with I. Okay? So these two pictures are completely analogous. But is that clear? I mean, I can try to even draw the analogous picture of these things, but it becomes slightly more complicated because now the picture has to be 3D. But let's try. So what I'm saying here is that at time t prime, so let's pick a time t prime. Yeah, this is fine. Let's call this time t prime, right? So at t prime, you have this line. And let's call this time t double prime. So at t double prime, you have this x. So what I'm saying is that at t prime, this function has to be a very specific function of x. So maybe that specific function of x looks like this. And at t double prime, it looks like another function of x. And maybe that function of x looks like this. And then, so here you join your initial and final point by all possible paths. You will do the same. You will join this line with this line via all possible surfaces, right? And here where it gets tricky to draw things because, well, there are no surfaces. But this can be a surface. But this is another surface. No, I'm getting confused. Where are the points? Oh, okay.
Here surface means states.
Sorry, can you say that again?
I have here surface means states.
No, so here, what does this line mean? It simply means that the value of q is varying according to time, right? So at t prime, value of q was this. I mean, so this direction is q. So at t prime, you are at q prime, then a path connecting q prime and q double prime is a line, right? Because you are drawing all the values of q at different times, and they become a line. Here it's the same idea, but I'm saying that there's another direction x. So at time t prime, you have some specific function of x. And this is the x-axis. So that function will look something like this. And similarly here, that function will look something like this. But at intermediate times, let's say we choose some intermediate time. At this time, again, your function phi, when you fix the value of t to this thing, is some function of x. And that function of x may look like this. So if you take all of these intermediate lines and join them, you get a surface, right? So that's what I mean. So this is one surface. But as I was saying, that there are many, many surfaces that you can add. This is some different surface, right? So,
But all surfaces are one-dimensional, right?
well, all surfaces are two-dimensional, right? It's like a sheet. And here each line was one-dimensional, but now each surface is two-dimensional.
Yes.
Okay. So here what we did was that in this case, so what we did is that we summed over all paths, and for each path, we computed a number, a real number, and then we summed over all of these phases. And that was our transition amplitude from q prime to q double prime. Here we will do exactly the same. We will sum over all of these paths, but now the paths are surfaces. And for each such path, we will figure out a way to compute a number. And then we will sum over all possible paths. This is the sum over all possible paths, or in this case, sum over all possible surfaces. And then again, we sum all of these phases, and then this will be a transition amplitude from this function to this function. Okay. So this is a big conceptual step. So let's make sure that you understand what's going on. So let's say, I will try to elaborate more about what these things will look like in this case, but let's see if this picture is clear. So there's one question. So in summary words, we are looking into the path of particle in 1D and 2D by taking the known informations like S, epsilon of X, T. I didn't fully understand the comment about 1D and 2D, but let's see. We are looking at the path of particle. It's no longer just a particle because, or trying to interpret in using the physical language of particle becomes a bit complicated here. because the thing that we now have depends on two variables. So usually it would be called a field. I mean, this is also a field, but it's just a field of time. So usually this is usually referred to as the position of a particle. But in this case, people would say that this is a field. But again, these are just language. It doesn't really matter. The whole point is that there is a function of x that evolves with respect to time. That's how we're thinking about it. Here, there was just a function of time that was evolving. Here, we have a function of x that depends on time, and this function is evolving. And at each fixed time, we can visualize this function of x as you would visualize any one-dimensional function.
Is it possible
Okay.
to connect higher? Is it possible to connect higher dimensional surfaces between 2 points like this?
No.
Or
Yeah, I mean, 2 points can only be connected by a line, and 2 lines can only be connected by a 2D surface.
okay, so if it will be 5D or 6D, I mean higher dimensional, like string theory or
Well, actually, so string theory has some similarities to this picture, but conceptually, it's a completely different thing. So maybe we will not discuss it at the moment. But what we can do is that instead of just having t and x, we can have more variables. We can have x, y, and z. And then we can compute the transition amplitudes from a specific function of xyz to another specific function of xyz. So we will say that sum over all field configurations such that at t prime, you have some specific function of x, y, and z. And at t double prime, you have some other specific function of x, y, and z. And then if you sum over all field configurations that satisfy these boundary conditions, you will have computed the transition amplitude from this function of xyz to this function of xyz. Okay. And this is what you would call a 4-dimensional field theory. And this is what you would call a 2-dimensional field theory. And because, okay, so this is, I'm of course saying that this is 4-dimensional because there are 4 variables. But because time plays a special role in this picture, right? Because notice that we're only imposing boundary constraint at fixed time. Sorry, was there a question? No, okay. So because time plays a special role, the dimension is often referred to as 1 plus however many other variables you have. So this 1 stands for time. So if you have t, x, y, and z, then you would call it 1 plus 3-dimensional. So this would be 1 plus 1-dimensional. Let me use some weird color. Not weird enough. And then here you would just call it 1 plus 0-dimensional, right? Because there's only time, which corresponds to 1 and nothing else. So basically, the point that I'm trying to make is quantum mechanics is 1 plus 0-dimensional QFT. So basically, everything is QFT. All that changes is the number of extra dimensions in addition to time. So in quantum mechanics, there's nothing else. In QFT, well, if you're doing, it depends on how many other variables you have. If you're modeling something in the real world, you will have 1 plus 3. Okay, so now we can get into the specifics of how to actually build these things, right? But I believe that you have already seen example of these kind of things. Okay. So what we have been saying is that for any path like this, where now path refers to something very generic, it's not just a line, but rather it's something like this. So for a 2-dimensional thing, this will be a surface. For 1 plus 3-dimensional thing, we can no longer draw these things. We just have to do it mathematically. So for any function, t, x, y, z, or we will from now on refer to it as phi x mu, where mu goes from 0 to 3, we have to figure out some way of producing a real number, right? So that we can compute these things. And so that's called an action. And also from now on, I'm going to assume that our Hamiltonian is quadratic in momentum, and the coefficient of the quadratic term is independent of position, so that we can integrate out momentum. So the action that we're going to write down is only going to depend on our field and its derivatives, not on the momentum variable that you have encountered in canonical quantization. So we have to produce some function of phi. And so now this is the real essence of physics. So how to produce a real number out of a field like this. And so now you really have to think about what kind of physical phenomena you are trying to model, because that will tell you what kind of action you should write down, because there is no unique way of writing down actions. We can make various assumptions about our physics, that maybe the thing that we are modeling has some symmetry. So for example, we will always assume that it has Lorentz symmetry. And then we have to assume that something about locality, that maybe the thing that we are measuring is local. So there are no long-range interactions. And by long range, I mean going out of your causal cone. So depending on the physical problem, you will have different kinds of assumptions that will lead to different kind of actions. But locality is something that's very nice. We most of the times we want to model local physics. And local physics will tell you that this should be an integration over all of these coordinates. And all of these coordinates collectively, we will refer to as spacetime. So this will be an integration over spacetime. And here what you will have will be at most quadratic in derivative if you want to maintain locality. So for example, something that you can write down, maybe it looks like this. Okay. But then you can add other things. Basically, you can add any function of this phi. You can add phi square with any coefficient you want. You can add phi cube, and you can add phi to the power 4. I shouldn't write g. You can add anything you want. Okay. So often you will see this kind of expressions that for some field phi, you start with a term that's quadratic in the derivatives, and then a bunch of polynomial terms in phi. So this ensures locality, but what about Lorentz invariance? We said that we want our physics to be Lorentz invariant. Well, again, so if you have studied a little bit of classical field theory, you will know that in order to write something that's invariant under Lorentz transformation, you should always use things that transform nicely under Lorentz transformation. For example, phi is a scalar, so it doesn't even transform under Lorentz transformation. So this is obviously invariant. But you can also use other representations of your Lorentz group. So for example, what are the representations of the Lorentz group? Representations of the Lorentz group are labeled by two half integers. Right? I think you have also had some discussions about this. I will just say a few words. So representations of the Lorentz group so they're labeled by two integers. Let's say m and n. Okay, two half integers. So 0, 0 corresponds to scalars. I think I'm spelling scalars wrong. How do I? No, probably this one. Okay. So scalar simply means these kind of things. So just some function that depends on all your spacetime coordinates. And the function itself doesn't have any index. Then you can have half
That's the
zero.
right spelling of scalar.
Sorry, can I say that again?
Yeah, that's the correct spelling of scalar.
Okay, good. Thank you. Okay, so then you have half zero, or you can have 0.5. So these are called left-handed while, right while. Well, you can have half, which are vectors, and everything else. We will not go beyond these things in our discussion. And at the moment, we will mostly talk about this, and I don't think we're going to have a lot of time to talk about this, but we will talk about this as well. And about this when we talk about gauge theories. But for now, let's focus here. So we just have a function of our space-time coordinates and nothing else. And with these functions, you can write down things that look like this. I mean, obviously, this is the number that you are producing out of such a function, right? So this is a valid candidate for an action. But this is by no means the unique candidate for an action. There can be other examples as well. But for now, this is a good one. Okay, let's see. So let's take a pause and see if there are any questions. Yeah, so please ask any questions, because we are making some conceptual leaps. So let's make sure that things are clear. Is it clear how we go from this picture of quantum mechanics to this picture of quantum field theory?
We're just increasing the number of parameters. That's all we're doing.
That's all we're doing, yes. Okay, so if there are no confusions, that's very good. And so just a comment. So we were more or less rigorous about deriving the path integration for this quantum mechanical picture, right? Because we started by discretizing time, and then we took a continuum limit. We can do the same here as well if we want to. So what you would do is that you would discretize not only time, but also this position x. Okay. So suppose this is the plane, this is the space-time plane where you have t and x. You can, okay, let's draw a lattice here. And you can say that these lattice points are the discrete version of your space-time, right? So recall that previously we had discretized time. So maybe I still have a picture somewhere. Yeah. So this picture that we were drawing. So here, this horizontal axis was the time axis. So this was our time, t. And we discretized it by picking specific time. And then we did some manipulation. And then at the end of the day, we took the continuum limit so that time became continuous. So we will, oh, sorry, not here. So we can do the same here as well. So you discretize space. And then for each value of this lattice, each vertex of this lattice, you have some value of your field. And at the end, you take a limit where this spacing becomes very, very small, and the number of points become very, very large. And in that limit, this will become a smooth surface, smooth spacetime. Okay. And the field that you had before simply becomes a function of your spacetime. Right? So because when time was discrete, you had a field with the value of time as an index. Now you will have field with the value of time and x as index. But when t and x become continuous, we usually just write it as a function of time and space. And that is this kind of fields. Okay. So this is just to point out that even though, yes, go on.
Why are you always taking continuum limit? Why?
Because
from the discrete, yes,
right,
from the discrete version, why?
Yeah, the reason is that the discrete version which involves finite sums of things, is a completely well-defined object. Okay, there is no ambiguity in the definition of what we mean by a path integration in the discrete scenario. However, the continuum limit is not usually super well-defined. We can do computations, of course, but if you want to be mathematically rigorous as to what it means to sum over infinitely many continuous paths, it is not usually well-defined. To kind of motivate this thing, we say that, okay, you start with the discrete and you take the continuum. But for example, if you want to do some explicit computations in a computer, I mean, how would you do it? You cannot parameterize all paths and do an integration over paths in computer. You have to realize this thing as lattices, which is a completely well-defined again. If you can program something, it is well-defined. And you can program a lattice model of a quantum field theory. And then this will have some parameters, and you can take the limits that those parameters go to infinity or 0, and then you get some numbers. And that really is, at the moment, I would say, one of the best definitions of what a continuum quantum field theory is. It's a limit of a discrete thing. That's why I'm highlighting that there is a well-defined discrete version of everything that we're talking about. And you can, once you have established the discrete thing, you can take the limits and get some numbers. Even if you are uncomfortable about the rigor with which you can define path integration, you shouldn't be, because there is an alternate definition. That's what I'm trying to point out.
Thank you, sir.
Okay. Now let's see. Let's take an explicit action which has this derivative term. And with the minus sign. There are various conventions about signs, so it's not super important. You can pick something you like. Okay, so this is a well-defined action for a scalar field in 4-dimension. I'm sure you're familiar with tensor notations, right? Now we want to compute the path integration. Integrate over all fields with this. We want to know what this is. And again, in principle, if you have finite time interval, you go from time t prime to time t double prime, then you have to impose boundary conditions. You have to tell me what this function looks like at time t prime. This will be some specific functions. And at time t double prime, again, this will be some other specific function. But as we try to argue in the quantum mechanical case, that if you allow this time t prime to be negative infinity and t double prime to be positive infinity, then there is really a unique boundary condition, which corresponds to the vacuum of the theory. And that's what we're going to assume from now on. So we will not worry about these boundary conditions. We will assume that we are imposing the unique boundary condition. Okay, so how do we compute these things? And okay, so this is a vacuum to vacuum transition amplitude in the theory defined by this action, right? So let's first compute the vacuum to vacuum amplitude. Also, we were just arguing that we should really put some additional fields, right? So in addition to this usual thing, we should also add this extra stuff so that we can later take derivatives and compute transition amplitudes with operator insertions. So we will do the same here. This is the action that we're actually interested in, but we will modify it by adding, let's say, some field j, again, completely arbitrary, and then phi. And okay, maybe I should write sj to remind us that we have added j. So this is what we want to compute. Right? So how do we compute these things? Well, first let's observe that here we can do an integration by parts for the kinetic term to put the derivative on the other side. This is the same as and I'm also going to do something. Let's not keep the half. Okay, I haven't done anything other than just an integration by parts. But then we can rearrange our action like this. All right. So the nice thing about this action is that it is quadratic in phi. And then inside we have some operator that acts on phi. Okay. And remember from our discussion on Gaussian integrations that if we are doing an integration of an exponent of an exponential where the exponent is quadratic in the integration variables, then it is rather easy to do the integration, even if the coefficient is imaginary. And this remains true even in path integration. And even the answer looks pretty much the same, which is not surprising because remember that we also argued that we can generalize a Gaussian integration to multiple variables with matrix operators. And the result that we get, this
Very
result,
analogous.
yeah, it's basically the same as the one variable result, right? You have something quadratic in the coefficient, you have some operator which is the inverse of this operator, and these numbers we will not really care about. And as we have been saying over and over, the continuum path integration is nothing but a continuum limit of these kind of things, where you have multiple variables, but you take the larger limit. So this result also remains the same, basically. So how do we identify different things? So we have something quadratic in our integration variable. Integration variable is phi. We have something quadratic in phi and something linear in phi. So the result, we expect that it will again be an exponential, something that is quadratic in the coefficient, j, and it will involve the inverse of the operator that appears here, right? So the tricky part really is to understand what inverse of this operator can mean, all right? And so basically, let me copy this formula. So this will be our reference. Yeah, cannot read this. All right. So if we compare with what's going on here, then we can try to guess what the integration of, what this integration should look like. It should basically look like, again, it should be something, the exponent of something, and that something should involve j and del square minus m square inverse and j, right? And here we had an integration, and this integration is really very similar to what you have here once you break it down into components, right? So here, for example, in components, you would write these as a double sum. Say ij, omega I, A inverse ij, omega j, right? This is what it looks like in components. And the summation over these indices is really analogous to this integration. However, notice that here you would have double integration, right? One xi, aij, and here j, and then sum over I and j. Here you only have one integration. That may seem like a difference, but if A is diagonal, then this is also a single summation. So we should think of this single integration or this single integration as something coming from a diagonal operator. So this operator is kind of like a diagonal operator. So at the end of the day, this may be a diagonal operator or not. At the moment, we do not know. But what we should expect is, in general, a double integration, right? Let me try to be a bit more clear. There should be an integration over, say, d for x, d for y, jx, and whatever the inverse of this operator is. And this should depend on both x and y. Let me write it this way. And jy, right? So this is the kind of thing that we expect to get by evaluating this integration, by analogy with this formula, right? So the task now, well, of course, one should verify that this is indeed what we get, and we will verify this. And we will, in fact, find by an alternate route what this inverse is. So let's do that now. So as I have been saying, that the difficulty here really is the inverse of this operator because it involves a derivative. If this wasn't a derivative, it was just some number or something like that, then we could just put this inverse and apply this formula directly. And we can get to an expression like that by using Fourier transformation. So let's define Fourier transforms of our variables. So let's call it phi, which will be a function of the 4 momentum k. Again, so k has 4 indices, k1, k2, etc., etc. D for x. Okay, and this is the inverse of the usual thing. All right. So phi is our original variable, and we are defining the Fourier transform of phi as phi tilde. All right. So now we can use this formula. So wherever you have phi in this expression, here or here, you substitute this formula. The reason why it's beneficial is that, so here you have a second derivative acting on phi. But if the second derivative acts here, okay, so once you substitute this phi of x, and you act on this thing with, oh, let's forget about the m part first. You act on this thing with the second derivative. The second derivative only acts on this exponential term. So what you get is just k squared. And to clarify, this is a Lorentz contraction, k mu x mu. Actually, it gets messy, so I will write k mu x mu as k dot x. All right. So by acting with del square on phi, you simply bring down a factor of k dot k or k squared. Okay, so this simplifies greatly the expression. So this expression written in terms of the Fourier dual variables will not have any derivatives. It will just have k squared. So I will just write down what you get at the end of the day. It looks like d for k. I think I'm writing 2 different symbols for phi. Let me stick to one. Okay, we'll find this. So this is our action. Up to some numbers, probably. Maybe there may be some numbers here. Okay, so what has happened? So our variable is now phi tilde instead of phi. And the coefficient of the quadratic term is now not a differential operator, just an ordinary number. And the linear terms, okay, you get 2 linear terms, that's fine, but there's nothing new. Now we can do this integration. So change our integration variable from phi to phi tilde. And when this action is given by this expression, it is easy to integrate. Using basically this formula. Maybe it will be good for you to do some of these calculations in exercises. Yeah, I will try to remember that. But so what you get is simply, as expected, you get an exponential. And something quadratic in J. But at the moment, we have the Fourier dual variables. Okay. So now you can go back to the original variables. So J and J tilde are also related by this kind of formulas. It's the usual Fourier story. And if you replace them by their Fourier dual variables, you do get a double integral. Let me write down the operator as delta for now, and I will write down what delta is momentarily. Okay, and this delta so is nothing but the Fourier transform of 1 over k squared plus m squared. And you get that simply by replacing these things with these kind of expressions. So you have two functions that you're replacing with this formula. So that's where you get two integrations from, this one and this one, with these two functions. And these two exponents combine to give you this. So after you isolate these two functions and these two integrations, all that remains is this. So this integration is literally the one that you already had. And this is just the k-dependent part of this once you replace them by their Fourier formula. Okay, so this is the result of this integration where the action is given by this formula. Okay, so it seems very easy, right? And it is easy. And the reason that it is easy is really because the entire action is quadratic in phi. If you had any terms that's higher order in phi, you would not be able to do this. And that's where interacting quantum field theory comes in. So this action where you only have terms that are quadratic in your field is referred to as a non-interacting theory or a free theory. And the reason is quite simple. So if you have an action that's quadratic, what is the equation of motion that you get? Again, I assume that you have already seen how to derive equation of motion from actions. So if you do it from here, the equation of motion that you would get is nothing but del square minus m square acting on phi is 0. I'm also setting this extra term j, which are called source, by the way, to 0 as well. So the point is that with a quadratic action, your equation of motion is linear. And the property of a linear differential equation is that the sum of two solutions is another solution. So what this means is that if you have two solutions of this equation, so you can think of the solutions as, you can think of the space of solutions as a vector space, which has a basis called a plane wave, a simple basis. And the plane wave solutions are usually identified with particles because they have definite momentum. But the point is that if you just add two plane waves, so physical picture in mind is that there are two particles, what you just get, the summation itself is another solution. So you don't create any extra term in your solution. And that's where this free terminology comes in, because two particles, you put them together, that's another solution of the system. So those two particles do not interact to produce some new complications in your solution, right? So this linearity of the equation of motion is the same as having no interaction. That's why quadratic action implies linear equation, implies non-existence of interaction. Okay. So far we have computed the vacuum to vacuum transition amplitude of a free scalar field with source. And now, by taking the functional derivative with respect to the source, we can compute vacuum to vacuum transition amplitude with insertion of operators. So it seems like I'm at the end of the time for today. So we will have to compute those transition amplitudes with operator insertions in our next class, where we will also discuss interaction. So what happens to this partition function if you add nonlinear terms interaction? So in other words, if we add here, let's say, a term that's phi cubed or phi 4, we can no longer compute this partition function like this because it's not Gaussian. So how do we do it? So then we will have to use some kind of approximation called perturbation theory. And we will see how to, so basically we will start from an action that doesn't have any interaction, and then we'll slowly, term by term, add corrections to our partition function based on those interactions. So that's the story for interacting fields. So we will do that in our next class. Also, unfortunately, I didn't talk about fermions. And so we will not talk a lot about fermions anyway, but I will point out, so how to compute this partition function for spin half zero and spin zero half fields. It's basically the same story. You write down something Gaussian, you compute the free partition function, which basically boils down to inverting an operator. That reminds me. So I didn't explain why this is inverse, because I will not explain it right now. I will either give it as an exercise, or you will be able to show it later, or I will show it later. So let me just tell you what I mean by an inverse. So if you act on, this is an x derivative with respect to the x verb. So if you act on this delta, which is also called a propagator. So if you act on the propagator with this operator, the one that we had in our action, what you get is a delta function. Okay, and this is kind of the definition of an inverse, because what is inverse in the matrix case? A matrix N is inverse to M if what you get is identity, right? If you multiply matrix by its inverse, you get the identity. And this delta function is the analogous of identity, because in index notation, you would write this as Mij, M inverse Jk equals to delta Ik, right? Sum over J. And this is exactly what's happening here. You may be a little bit confused about the summation. Why isn't there an integration then? Well, you can put an integration and make it look exactly like this. Maybe that's for an exercise. But the point is, this is the continuum version of this equation and nothing more, which identifies this as the inverse of this. Okay. Yeah, probably this will be exercise. So let me stop here. And if you have any question, I can spend some time trying to answer them. And then we will pick up from here and discuss interacting quantum field theory in our next class. So I will stop.